All right, let's talk about data structures and algorithms. You know, when you're just starting out, it can feel like you're standing at the bottom of a huge, intimidating mountain. But here's the thing, like any mountain, it can be climbed. And today, that's exactly what we're going to do. We're going to map out the entire route for you, from base camp all the way to the summit. So let's get our gear and start this climb.
And this right here is why we're making this climb, seriously. This isn't just about acing a coding interview. It's about a fundamental shift in how you think. It's the difference between being a coder who just gets something to work and an engineer who builds elegant, efficient, and scalable solutions.
I get it. It's the big question, right? You look at all the topics, arrays, trees, graphs, dynamic programming, and it's just overwhelming. It's so easy to get lost. Well, that's what this is all about. We're going to give you that clear step-by-step path forward so you know exactly where to put your feet.
So, before we take our first step up, we need to survey the land. We need to understand why this journey is so absolutely critical. This is the foundation, the bedrock that everything else is going to be built on.
This slide really gets to the heart of it. It's all about a change in mindset. See, a coder's first question is, how do I make this work? An engineer, on the other hand, asks, okay, why does this work, and is it the best possible way? Is it optimal? That one little question, is it optimal? That's the core of what we're talking about today.
So, how do we even talk about what's optimal? We need a common language, and that language is called Big O notation. Just think of it as a way to grade our code's efficiency. It lets us predict how our solution is going to behave when we throw a ton of data at it, way before we even run the program.
And this is where the rubber meets the road. Look at these numbers. For 100,000 items, a decent linear algorithm, it's done in milliseconds. But a less than optimal quadratic solution, we're talking hours. This isn't a small tweak. This is the difference between an app that flies and one that completely crashes and burns. It's huge.
Okay, so we get it. The stakes are high. Now it's time to pack our bags and get the right gear for the climb. We got to choose our tools wisely and really understand the environment our code is going to live in. And the first piece of gear is your programming language. Now, for learning all this stuff, and for most technical interviews, Python is what you want. Why? Well, it's simple. It has low verbosity. That means you're spending your brain power on the logic of the problem, not fighting with complicated syntax. It just gets out of your way.
And here's another key piece of gear, understanding computer memory. You've got two main areas. The stack is like a neat stack of plates. It's super fast, but you can only grab the one on top. It's for quick, temporary stuff. The heap, though, that's like a big open workshop. It's where we build and store our larger, more complex data structures. Really getting this difference is crucial, especially when we get to recursion.
All right, we're all geared up. We're at the trailhead. It's time to start the ascent with the most fundamental building blocks of all, linear data structures. These are the ones where data is just organized, nice and neat, one after another.
And we're going to start with the most basic one, the array. An array's superpower is its instant access. Because all its items are stored right next to each other in memory, in one continuous block, the computer can just jump straight to any element it wants. No searching required. It's the foundation of so much. But, you know, knowing the tool is one thing, you gotta know how to use it. And for sorted arrays, the two pointers technique is an absolute game changer. It's a clever trick where you move pointers from both ends of the array toward the middle, which can take a slow, clunky solution and make it lightning fast. Next up, linked lists. And these present a really interesting trade-off. We lose that instant access we had with arrays. But what do we gain? Incredible flexibility. We can pop a new item in or take one out from anywhere in the list super efficiently without having to shuffle everything else around. And the classic pro move for linked lists is the runner technique. You have two pointers, a fast one and a slow one. The fast one moves twice as quickly, and just by doing that, you can solve some really tricky problems, like finding the exact middle of a list, or even figuring out if you're stuck in an infinite loop, all in one go. It's super elegant. Now, if there is one single tool you absolutely must have in your engineering toolkit, it is the hash table. It is a work of genius. It uses a special function to turn any piece of data into a direct memory address, basically giving you the best of all worlds. Near instant time for finding things, adding things, and removing things. It's like a magic trick for your code. We've now climbed through the linear paths, which is great progress. But as we get higher up the mountain, the terrain gets more complex. Let's take a quick look at the nonlinear structures you're going to encounter up ahead. So first up, you've got trees, and these are exactly what they sound like. Anytime you have data with some kind of parent-child relationship, like the folders on your computer or a company's org chart, a tree is the perfect way to represent that structure.
And then you've got graphs. These are for when things are connected all over the place, in a big web of relationships. Think about your social network, where you're friends with lots of different people who are also friends with each other. Or think about Google Maps modeling all the roads between cities. That's a graph.
Okay, so knowing all these data structures, it's like a rock climber knowing all the different types of handholds. It's essential, but it's not the whole story. The real skill, the art, is in how you actually climb. So let's talk about the skills that separate the pros from everyone else.
At the end of the day, it really boils down to 3 core meta skills. First, dry running, proving your code works without even touching a computer. Second, spaced repetition, a system to actually remember what you learn. And third, the holy grail, pattern recognition. Look, dry running isn't just staring at your code and hoping for the best. It's a discipline. You get out a piece of paper, you make a table for all your variables, and you walk through your code line by painful line, updating the values. It is, without a doubt, the best way to catch bugs and to truly understand what is happening.
The human brain is actually designed to forget things. It's a feature, not a bug. Spaced repetition is how you fight back. You solve a problem, then a couple days later, you solve it again from scratch. Then a week later, you review the logic. By spacing out your reviews like this, you're telling your brain, hey, this is important. Keep it.
And that brings us to the summit. This right here is the whole point of the climb. Please do not try to memorize hundreds of specific solutions. That's a losing game. The real goal is to learn to see the underlying pattern. You'll find there are only about 15 or 20 core patterns, and almost every new problem you see is just one of those patterns wearing a clever disguise.
So, there you have it. We've given you the map, you have your gear, you know the techniques the pros use. The entire path from coder to engineer is laid out right in front of you. The only question left is, are you ready to take that first step?